Alright. As you've noticed, we're now fully into the topic of optics, and optics obviously has to do a lot with light. Um, there, there's going to be a whole section after your midterm break where we're going to talk about light more theoretically. Right now, we're talking more about light as a tool, as how we see it, and what utilizations we get out of it. As like a normal human being, and then we'll talk about after the break. We'll talk about it. What does a physicist get out of light? And that's a little bit more theoretical, and we're going to get into like light as a wave, light as a particle, quantum numbers, packets, and things like that. So it's going to become a bit more abstract, but today it's still very much practical. I just briefly still have to mention to you that if light was to be seen as only a particle, and if I were to shine light into this kind of object that's opaque, except it's got two slits where light can travel through, if light was a particle, what I would see on the other side is just these two lines, right? And that's not necessarily the case. In fact, that is not the case. And so what actually is happening is if you have light going through these two slits towards the same environment, what you end up seeing on the other side is multiple lines. And this pattern here is called a diffraction pattern. All right, and that's because light diffracts, and that's one of the properties of light. When you guys learned this previously, did you guys hear? You guys definitely heard the terms refraction and reflection. The other two things were diffraction and dispersion. You guys hear those two words? Just hear the word, not actually have it. Yeah. So this is the property of light that describes diffraction. The fact that if you send it through a slit, it kind of not diverges, but it becomes a wave, and you'll see in this system here. So if this was the light source and the light's emitting in all directions, and there's an opaque barrier here with a slit that allows light to go through, what happens is that I don't have another diagram. What happens is that from here, you'll have another wave that's being created. Like that. Okay? And that's the property of light, what we call diffraction. Light is able to do that. Have a look here. Diffraction. And it's not only applicable to light. In this case, this is applicable to all things that behave like waves. All right. And I showed you. Did I show you the guy who had his slinky hanging down and you put a microphone in it and he was making like sounds with it? Okay, so I showed you guys that one, but I have another one to show you. Let me just get through this slide real quick. It's the same idea. So if you have a wave source coming in this direction, you can see the wave continue passing through. And then here, a new wave is being created. And there's diffraction patterns, depending on how many slits you have and how strong the source is and how distant the screen is. We'll do some math about that in a few weeks. But you'll have different lines. If you remember, you'll have there's a way to calculate how many lines you'll see and what the brightness of each line is going to be. All right? Again, that's called diffraction. So this concept's not for light, but for sound. We talked about it. We already showed you this video, so that was a sound effects video. And this is another video which I find really interesting. And this is sound that's diffracting.
There's many things about this place that are unusual, and one of the things that I
pause you.
There's many things about this place that are unusual, and one of the things that I find very fascinating is how quiet it gets. It's the quietest place. When the wind is down, when there's no wind, it wakes you up in the middle of the night because there's no wind and there's no sound at all. And if you walk out on the ice, you can hear your own heartbeat. That's how still it is. And you can hear the ice crack, and it sounds like there's somebody walking behind you, but it's just the ice. It's sort of, these little stress cracks moving all the time, because we actually, right here, we're on ocean. We're not on solid ground. So, and you can hear the seals. You can hear the seals caw, and it's the most amazing sound. They make these really inorganic sounds. They sound like, I don't know, Pink Floyd or something. They don't sound like mammals. They definitely don't sound like animals. it's really out of this world, I can say that.
You get used to a surface being solid, and you sort of think in your mind that you're on land. And then all of a sudden you'll hear the sound coming up through the floor. You'll hear the chucks and the whistles
And the booms.
and the booms that come, which are you realize there's a whole world underneath you. The seals are moving and competing and fighting beneath you under the ice while you're here sleeping in a tent or working in a lab hut.
Can't buy these little 3,000 year things. Anyway, that's a very interesting example of diffraction happening. It has to do with the relief of the ice, and it has to do with the ice underneath what they're standing on, and and like the just the underground geometry, topography, the underwater topography. All right, back to this. In terms of what you guys need to know for this topic is really just how to describe anything that could be diffracted, right? So it can be seen as a wave and it goes around corners as a wave kind of thing. So if I were to say that there's a light source here, right, shining in that direction, right, can you detect any light over here? Yes, you can, because light is not just going to go that way. It comes around the corner and comes around the corner and creates a wave like this. And therefore, yes, there is some illumination around that corner. It might not be a lot, but it still is. Think about it. If you're in your bedroom and you have the light on in the hallway, let's say, and your door is closed, you still see the light from underneath the door, and it's kind of illuminating your entire room, right? And it makes maybe if you're very sensitive to light, that might make it harder for you to see. All right, that's that. That's diffraction. Any questions on that? So qualitatively, that's what you need to understand. And we're going to get a bit more quantitative with mirrors. And that's obviously having to do with the law of reflection now. And so that's the second property of light, and that property is reflection, that light can be reflected. Whether you consider it to be a particle or a wave, this law holds regardless. And again, all waves can be reflected. So we're talking about light now, but then you can apply this to sound, and you can apply this to water waves or anything like that. The law of reflection is very simple. Okay? The angle at which the wave hits a reflective surface is going to be equal to the angle at which it reflects off of that surface. Okay? So here it is that the law of reflection is that the incident angle is equal to the reflected angle. And I'm going to use a lowercase r for this on purpose. I want you guys to do the same thing because I'm going to use an uppercase r for reflection. Okay? So it's the incident angle is equal to the reflective angle. And this is the angle with the normal line. Right? So if this bottom part here is the reflective surface, right? It's not this angle that I care about, it's really this angle here. Right? That might not be important so much for reflection, but that is super duper important for reflection. right? And you can make it, you'll make calculation mistakes if you use the wrong angle. Oop, I wrote it here, so I'm just going to move it up here so that it doesn't block anything. So this is the law of reflection. Incident angle is equal to the reflection. That kind of makes sense because it's the same, but in the opposite direction, kind of like a mirror. Now, if this was behaving like a wave, and it also is, and I were to draw it like this, all right, there's my wave coming into the mirror. And now it's going to have to reflect. How would that look like? Would it start off drawing, I'll draw two options. I'll draw one in red and one in blue. Which one would be right, the red one or the blue one? Blue one? Now think about a wave, right, on a string, and it's colliding with a fixed object. What happens to the wave after it collides with a fixed object? It's inverted, right? So which one is it going to be? Blue. And so this one is going underneath, and then it goes back underneath, or does it go above now this time? So remember the string, it would go, let's say like this, hit the barrier that's fixed, then is it going to come back up or down? Down, right? So if that were the case, and this one is going underneath it, it hits the barrier, that means that this one has to be the red one, has to be above. So the blue one is going to. Make sense? We have two types of reflection, right? And we call them specular and diffuse reflection. Specular is like on shiny objects, diffuse would be on non-shiny objects. So if I were to say, this table, is it reflecting light, yes or no? Yes, absolutely, it's reflecting light. Is it specular or diffuse reflection? It's diffuse reflection. If I were to say, if I can see, like if I were to look at this on an angle and I can't see your face in it, then it's diffuse reflection, right? If this was a glass table, right, and I looked at it on an angle, I can see all of you guys in the reflection of the table. That would make it a specular reflection. So if I were to say, I don't know, I don't see any specular reflection here. Oh, I got it. If I use this, and I could, let's say, try to look at you guys, would that be specular or diffuse reflection? Specular, right? If everyone's got their phone out and you can look at it, you can see, like, if you look at it on an angle, you can see me kind of, you look at the right angle. That would be specular reflection. And the reason for that is because the light rays, they all are parallel. So the way they enter is going to be the exact same way they reflect. Whereas on a diffuse reflection, the surface is really bumpy, and it might, this table might not look bumpy, but if you looked at it under a microscope, it's super duper bumpy. And that it's still following the law of reflection. It's just that the surface is no longer all on the same plane, right? So some of them is angled upwards, so the law of reflection is at that exact moment applies differently than if it were just like a speck next to it. So that, at that point, you can't resolve an image from that diffuse surface. Hey! All right. Yeah, so kind of makes sense. The term resolution is really important. We might not talk about it today, but resolution is really how sharp an image is. And it really only is sharp if all of your light rays converge into a single point, right? Or converge correctly to a single point. And you're going to get that with this, whereas you're never going to get that with this. Okay? We'll talk about that maybe next week. Any questions on this? Okay, so quickly, that was reflection. Now we're going to do refraction, and we're going to use capital R this time. And this uses Snell's law, if you guys remember. And Snell's law, it relies on a characteristic property of substances called the index of refraction. When I say characteristic property, does that ring a bell? Specific for each material or substance, whatever. But yeah, that's the right idea. So for example, boiling point is specific to any substance, right? Like the boiling point of water is going to be different from the boiling point of mercury, is going to be different from the boiling point of I don't know, calcium, right? So every substance has its own specific boiling point, just like every substance has its own specific index of refraction. It has to be translucent, right? So it cannot be opaque. So if it were opaque, it would not have an index of refraction. For example, this table would have no index of refraction. Or if it does, it's so high that it doesn't really matter what it is. Right? Now, what we need to understand for refraction is that light speed, right, depends on the medium it travels in. Exactly like sound, exactly like other waves as well. So let's say you're talking about sound, and we said the speed of sound in air is 340 meters per second, right? The speed of light in air is whatever, 3 billion or 300,000 kilometers per second, or 300 million meters per second. Yeah, there you go. But that's just in air, or very close to being in air, or in vacuum. But if you put it in water, it slows it down. Put it in glass, it slows it down. And so it depends on which medium it's in. So we have this equation here, and this is like the super equation at the bottom. You might be used to this one, that's Snell's law equation, but I need to explain what this is for you guys. This is to determine what the speed of light is going to be and represent the index of refraction. So let's come up with an example. So I have here. Let's say I have air here, and air has an N of 1.00. That's air, not all air, and this is water, which has an N of 1.33. Right? If I have a light ray that comes in with a velocity of 3.0 times 10 to the 8 meters per second, right? What's going to be the velocity of my light as it enters the water? Okay? So you would just use this equation here, and this is the incident ray is going to be 1, and the refracted ray is going to be 2. So this is going to be incident, and this is going to be refracted. So we have N1, P1 over N2, and give us the 1.0 times 3 times 10 to the 8 meters per second divided by 1.33. That's going to be equal to 2.35. Is that right? So light slowed down when it entered water. That makes sense. Now, imagine another example. Imagine another example. This time, you're going at an angle. Okay? And this angle is a normal. We're going to call, let's say, 30 degrees. And we're going to say this is an N of 1, and this is an N of 1.33. So it's going from air into water, and it's going to slow down. Okay? I'm going to pause this for just a moment, and I want to ask you guys another question. All right. Supposing we're 14 people here, you're all best friends and you're holding hands. Okay? And as you're holding hands, so I'm going to represent everyone by a dot, right? Except I don't have space to draw 14 dots, but you're 14 people, you're all holding hands, and you're moving towards this area here. And over here is asphalt. On this side of the line is asphalt. On this side of the line is sand. Okay? And you're all holding hands and you're running because life's good, and running in the field of asphalt towards a field of sand is what makes you happy. Anyways, you're going in that direction. All right. First of all, can you run faster or slower in sand? Slower. Okay, so slower in sand, kind of like air into water. So you're going in a direction, and you guys represent the wave front of light. Okay, light is a wave. That's how it works. So now you're getting closer and closer and closer. So everyone's moving in this direction. You're all running at the same velocity. So if you're running at the same velocity, are you still going to be, if you're right here, is this and this going to be parallel? Yeah, because everyone's running the same velocity, right? And then you're going to hit the sand, all right? So what's going to happen is some of you are going to reach the sand faster than others, right? And so now who here is running faster and who's running slower? These guys are running faster. These guys are running slower. Do you ever try to walk with one leg taking 2 steps and the other leg taking 1 step? What happens? Turn, right? So that's exactly what's happening here. One side of you guys is running faster, so the velocity there is faster. The velocity here is slower, so you're going to have a rotational motion, right? And so these guys are going to go slower, and therefore the whole group is going to rotate. And now once you're inside, you're now facing a different direction. And then you're going in that direction. Once you're all inside, now you're all running the same speed again, and at any point you're always going to be parallel. So what happened now is that your lights came in. That's, you guys, this is the whole metaphor here I was going for. You guys came in, hit a slower medium, and you bent inward. Sounds good? So if this was you guys running your field of asphalt, and then hitting the sand, the angle at which you're going to come out is going to be greater or less than 30 degrees. It's going to be less than 30 degrees. Let's figure out what this angle is. We've made a prediction. Prediction is less than 30 degrees. So now we have to use the actual Snell's law, which is N1. Come on. It's not working. There we go. N1 sine theta 1 is equal to N2 sine theta 2. You want to be in degrees for this. And we have a value that we need except for theta 2, right? So sine minus 1 of N1 sine theta 1 over N2 is equal to theta 2. So give me a value for that, please. How much? 22? 22.1? I'm out here at 22. 22 degrees. Now this is nice. I think you guys understand this. I'm going to ask you guys to do the same thing now, except you're running from sand into asphalt. So these people are always running at the same speed until you hit the the asphalt rather. And now these, the ones who cross the asphalt first, are they going to be running faster or slower? So these guys are going to run fast, and these guys are still running slow. So in which way is it going to rotate? Away from the normal. So if this is the normal line, Is it going to be away from the normal or closer to the normal? Away from the normal. So what's going to happen is everyone's going to rotate this way, and you're going to end up looking like this. And then you're going to have this in your angle. Okay? So let's try that here. Just reverse all the numbers and see if we get an angle greater than 30. The only thing that you're reversing is N1 and 1.33. And I have an answer? 42? You're all okay with that? Greater than 30, it's what I was expecting. And so yeah, so your wave is now traveling in a medium that's faster. It's going to be deviated away. Now, I'm going to ask you a different question. We're all running faster now, and so we've deviated away from the normal line. And now we're going to come back because there was only a strip of asphalt, and from the asphalt, we're going back to sand. Right? So now we're going to do that. Are we going to get closer to the new normal, or are we going to get further away? Closer, right? So now, let's say we're entering at an angle of 42 degrees. Either the normal, it's the new angle of 42 degrees, right? Because that's what we calculated. And we're entering back into sand. I want to know what the new angle is again. So it's going to be less than or greater than 42 degrees. Less, right? Okay, so let's calculate it with those numbers again and see what the number is going to be once we go back into sand. I think it's back to 30. Good guess. Confirm your hypothesis by punching in the calculator. You guys got 30. Same angle. All right. It's not a coincidence that you ended up back at the same angle here. Just doing the same equation, not backwards. So of course you're going to get back to 30. And last question I have for you guys about this is why didn't this change its angle when it went straight in? Who's my analogy of that? Okay. Exactly. So every particle of the wave, or every point of the wave, because light's not really made up of particles, it is a particle. All the points of the wave are entering the medium at the same time. So if they're entering at the same time, no one has a chance to go faster or slower before the other, and everyone slows down at the same time, or everyone speeds up at the same time. So the light continues going in a straight line afterwards. Okay. Sounds good. Let's say I had a light source here. Oh, first of all, the light source shines in all directions, right? As long as it's not being covered in one of the directions. In this case, it's not. right? And I have some medium here that's it's a translucent medium, and there's, let's say this is water. And the light's coming in this way. So this light ray is going to go straight through. However, this light ray is not going straight through, right? So if I were to be looking at the light bulb from here, the light bulb would look normal, right? That's an eyeball picture, by the way. Every time I draw this, my students are like, is that an A? Why did you have an upside down A? That's an eyeball. You guys get how that is? There's a little iris, eyeball, eyelashes, lower lashes. If you want, there's your nose, there's your mouth, there's your chin. Okay? So there I am looking at the light bulb. I see it normally. All right. However, if I were to look at that same light bulb, but over here, looking at it in that direction, then I would not see it normally. Okay, I would see it kind of maybe out of position. Okay, and so it's going to be different the way you look at it. So now, have you guys ever heard of the Spearman like situation? Yeah. Yeah. 30 again. So this time I did n1 sine theta 1 is equal to n2 sine theta 2. Right, and this was now the new first medium is the water, so it's going to be the 1.33 sine, and the incident angle is 42 degrees because that's what we calculated. And 2 is now air, so it's 1.00, and it's sine theta 2, and this is what we're trying to solve. So if you were to solve for theta 2 here, you would get 30. Okay? Oh, I think I know why. Let me restart here. So, here's 30 degrees. We said that this angle here is 42 degrees. This is air. This is water. Now we're going like this. This is the new normal. All right. Now that 42 degrees is close here. So it should work, 42 degrees. And so therefore it's going to give you an angle here. This angle should be 30 degrees. Yeah. So why? Still, no, it has to be the incident index of refraction, which is the index of refraction. I believe that you guys get 62, but what am I right? What's that? Yeah, I have to switch those around, but why though? I know that mathematically, if I switch them around, I'll get the right answer, but physically speaking, that doesn't make sense. You have to do the complementary answer. Oh, it's water to air. Okay, got it. Okay, that's probably why. But so then here, what would my angle be? Oh, so here would be a lesser angle, right? Okay, got it. So what would the angle be here again? 21, you guys said? 22? 22, 22, and then that should work. I think I was just mixing up two examples. But the formula is correct. That's how this would be. Okay, what was it talking about? I was looking at it at an angle, but then I was about to make a point about something. Oh yeah, the spear fisherman's experiment. Have you guys ever heard of that? Yeah, exactly. So when you're spear fishing, just in case you ever decide to do that, you take a spear and you're supposed to spear the fish. if you're on an angle and you see a fish, what you're actually seeing is not where the fish is, but where the fish's image is, right? Because there is some refraction that's happening. And so you want to aim a little bit off. Now, if you're right above the fish, it makes spear fishing a lot easier. So that's what ends up happening. So you go into like shallow waters and you walk like at ankle length deepness, and then you spear fish directly downwards. And the reason you do that is because there is no change in angle when you're looking at it directly down. So like you guys have seen that when you have a straw in a glass cup, that it kind of like deviates a little bit. That's all the same principle. Any questions? All right, so we're going to talk about the critical angle. And I want to remind you guys again about something that we just did. Okay, so we said that the angle increases when you go from an area that's slow to fast or from fast to slow. When does it increase angle? So to go back to notes if you don't remember. From slow to fast. So if your light's going from a slow area to a fast area, right, it's going to deviate away from the normal and your angle is going to become increased. Now what happens, let me just draw that example there. Here's my normal line, and here we're going to call this slow. We're going to call this fast. So we have some angle here, and this is going to deviate at some angle bigger. There's your incident angle, and there's your refracted angle. We're going to say that the refracted angle is greater than the incident angle. So if I were to continue increasing this angle, so if I just increase it a little bit, this would deviate even more, right? Eventually, as I get this angle just big enough, I will get a reflected or a refracted angle that is exactly parallel to the medium. So I have a refracted angle of how many degrees? If it's a refracted angle like this, what would be my refracted angle? It would be 90 degrees. That is what we call the critical angle, all right? And it only works when you're going from slow to fast. So let's write that down. Only works from slow to fast. All right, and so we can use Snell's law, which is n1 sine theta 1 equal to n2 sine theta 2. Like that. And we said that, yeah, correct, has to be. Otherwise, you can't get a critical angle. One. So we want to know at what angle, what incident angle, angle 1, do we need to use in order for the refracted angle to be 90 degrees, right? So we'll say that n1 sine theta, and when this angle is going to be called a critical angle, I'm going to write theta c, is equal to n2 sine 90 degrees. What's the sine of 90 degrees? 1. Okay, so that means we have n1 sine the critical angle is equal to n2, and therefore sine of the critical angle is equal to n2 over n1. Therefore, the critical angle is equal to the inverse sine of n2 over n1. So far, so good? Let's say I'm underwater and I'm looking upwards. What would be the critical angle? So you did that. The critical angle is equal to inverse sine of And 2 is water or air? Air. And it's got 1.00, and water has a index of refraction of 1.33. And so for this, you found that the angle was, Maxime, what did you get? 48 point. No, it sounds like you got the same answer. What did you get? 48.75. Okay. So now what happens? I have to put it behind me. So you're looking up at this, and you're not seeing what's happening on the other side anymore, right? So if you look up, what do you see? Let's take a video. Let's look at a video of this, because it's pretty cool.
Shedding Light on Refraction is the 4th video in the groundbreaking Shedding Light series of education.
Just go back real quick. I'm not sure if this video is appropriate or not. I just pulled it up. So just look at this. We're looking at him from air into water. Look how his layers are. Right? So because we're looking at this on an angle, it looks like there is some kind of right water. Obviously, that's not visual proportion. Let's see if there is an example of what I'm talking about here. There was this great video I saw the other day. I wish I could find it. Give me a moment. Oh, that's a cool video, actually. We can use this after. It's so trippy, that video. I really want to show you guys. Okay, let's watch this video while I try to find it, because I remember seeing it on my phone.
Demonstrating optical phenomena in the classroom can be difficult. The trouble is, light beams are invisible. The normal scattering agents such as chalk dust are messy and can cause other problems in the classroom. The laser viewing tank allows students to see and manipulate light beams in a lab group setting. These tanks act as student workstations, so you can set up a bunch with little time or fuss. When I aim a laser into the tank filled with pure water, the beam can barely be seen. When I add a small amount of scattering agent to the water, the beam becomes highly visible. Some light is reflected from the agent's particles as the beam passes through the water. And we're going to dim the lights so you can see what's happening. Next, I'm going to aim the laser down toward the water at an angle to see refraction in action. Look how the direction of the beam changes when it enters the water. Set the tank at the edge of the table and aim the beam upward to see refraction again. If you increase the angle of incidence by aiming the beam through the water from the side of the tank, you will observe total internal reflection. When a source of white light is sent through the tank, the light appears blue from the side because the short blue wavelengths are scattered more than any other. Looking through the end of the tank, the light appears to have a reddish tint because all of the blue wavelengths have been filtered out through scattering. You can also use diffraction gratings with different numbers of lines to observe interference patterns. Look at the well-defined maxima. There are so many characteristics to explore. Students really have a great time exploring the phenomena of waves with this tank. It really makes science fun.
Distract you while I talk. it's just a GIF, and I say GIF, not GIF. So you can see like, there's no way, because it's a GIF, I can't forward it or rewind it, but you can see that you're looking up at the water, but you're not necessarily seeing all of that. Right now, everything is just reflecting. It's like you're in a tunnel. But as you get closer to the surface and you start to change your angle at which you're lower than the critical angle, then you start to see what's going on the outside. But otherwise, because everything beyond here, you're looking at it at a very steep angle, none of the light that you're getting is coming from above you. So what ends up happening is that you look like you're in a tunnel. It's pretty trippy. And this phenomenon makes it so that diamonds are expensive. And you know, have you ever gone or seen one of those movies and there's like whatever diamonds and there's like that jeweler who takes a little magnifying glass and looks inside to make sure it's real? What they're looking at is actually the critical angle. I can close this now because it's going to distract me. What you're looking at is actually the critical angle. So they'll look at which angle the diamond is going to reflect. Because it's a characteristic property. Only diamond is going to have that beautiful angle that makes it shine a lot more than, let's say, like glass or zirconium or anything like that. So what ends up happening is, you have the diamond. Here's my generic diamond, right? And here's my zirconium. This is my fake one. So fake, diamond, real diamond. And what they're looking for is at which angles it'll reflect. So they'll shine light into it. And then what a diamond will do is it'll actually, because of the index of refraction is so high, the critical angle is actually quite low. So that's basically a lot of angles. Light's going to reflect inside. So light's going to do this, 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 and it's going to come out at an angle that's like when it's finally perfect, but it's going to come out more brilliant because of the way the diamond is shaped. And because of the high index of refraction, light coming from everywhere is going to bounce, 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 and it's all going to come out at the same time. So it's going to appear more shiny, more brilliant. And that is what makes diamonds so like precious, if we're talking about in terms of physics. But I mean, no one's really looking at their diamond rings this way. They just like it because it's rare and somehow shows that your husband loves you. But let's not get into that. But in a fake diamond, it'll be like, because the index of refraction is much lower, right? And the light's going to come out much easier. So light's actually, if the light's coming in at different parts, they're all going to go out at different parts because the diamond is not shaped in such a way to increase its brilliance. So here, if you're shinier than something like this, right? The light comes out much easier this way. That phenomenon, that whole phenomenon is called critical angle. And the fact that it reflects inside is called total internal reflection. Let's go ahead and write that. Okay. So assuming I have some medium like this, all right, and I have air, and here I have some material that has an index of refraction of 1.5. If I want total internal reflection to occur, is the ray going from down to up or up to down? Down to up, because it has to go from slow to fast. So let's say here, I have an angle of 75 degrees, right? I want you to calculate for me, actually, no, I want you to draw for me what the refracted ray is going to look like. But you're going to need to calculate it first. Make sure you're in degrees. Someone tell me what they got? Error, right? That makes sense because don't forget, at a certain angle, this is going to give you a refracted ray of 90 degrees. You can't refract greater than 90 degrees, so it's going to give you an error because mathematically you can't do the inverse sine of a number greater than 1. All right, so is that right? Yeah, you can't do an inverse sine of a number greater than 1. Now, so that means that something's going to happen here. Let's figure out what the critical angle is. All right. So remember, the critical angle is equal to the inverse sine of n2 over n1. And in this case, n2 is 1 and n1 is 1.5. What do you guys get? How much? 41.8. Okay. So the critical angle is at 41.8 degrees. That means at any angle greater than 41.8 degrees, we have total internal reflection. Right? And so therefore, if I want to draw my ray diagram now, no light is going to go through that medium at all, right? So none of my light, none of this light is going to go across the medium. It's all going to reflect. It's going to act like a mirror. And if it's acting like a mirror, my reflected angle has to be equal to my incident angle. And so it's just, if it's 75 degrees, it's going to reflect at 75 degrees. Next time you're underwater, look upwards and observe that. Perfect. Any questions on this? Remember the term, that term is quite important, total internal reflection, right? So I'll be like, I'll ask you a question or I'll draw you a shape and I'll say how many times will it bounce off of this shape before the ray can continue. So for example, I haven't worked this out on my own, but you can work it out. So let's say I have a rectangle like this and I shine, this is let's say 1.5, the outside of it is 2.0. So the ray is coming in at some angle. You're going to, because it's going to be closer to the medium here, you go inside, and then get closer, and then here is going to come outward. But at some angle here, you might get something that looks like this, and then you might have to reflect it, reflect it, reflect it, then it might finally go out there, kind of thing. For your lab tomorrow, you're going to need to know this, because there is a question on critical angle and total internal reflection. Any questions? Good. All right. So let's move on. So remember, we did diffraction, we did reflection, now we did refraction, and this is the last one. No, this is not the last one. This is still refraction. The last one is. Let's actually go through this because it's quite interesting. Before we get into the last one, so we talked about how waves, when they reflect, they invert, and how they go through. They don't through. And similar could be happening with sound, right? So sound, remember, the speed of sound changes depending on the temperature. Does it go faster with higher temperature or slower with higher temperature? You guys remember? Faster with higher temperature, right? Right? Because there was like 0.6 degrees, 0.6 meters per second for every degree Celsius. Did I show you guys that relationship? This is one of the PowerPoints. And so if you have sound going in that direction, right, and you reach an area that's colder, right, it's going to slow down, but it's slowing that at an angle. So you can now imagine that as kind of a situation where the incident, sorry, the refracted angle is smaller than the incident angle. And the same thing for warm air. So if you want so this is the example here, is pretty cool. If you want your sound to travel further in a warm air environment, you would actually point it upwards because it's going to have a tendency of going down. But if you point your sound upwards, it has a higher, it's kind of like projectile motion, and it'll come down slower, and then you'll reach it further. If it's cool air, you can see here that this dog doesn't hear where the sound is coming from because the sound is going upward. All right, now this is the last one, and this is dispersion. And dispersion is kind of like refraction, but it relies on the fact that light is made up of different wavelengths, and that each wavelength travels at a different speed, right? Here we have the UV spectrum. I think at this point, I'm going to ask you guys to just memorize this. You do need to know, this is what you need to know about, all right? Which end of the spectrum has high wavelength or low wavelength? So if there's a high wavelength, there's big waves, and so big waves are going to be over here. So look at the wavelength is in like 10,000 meters. Each wave is 10,000 meters a month. That's crazy. And here, that's the short wavelength. Each wavelength is 10 to the minus 14 meters. So those are really incredibly tiny. And these are called high energy. On this, sorry, the smaller end, those are called high energy. Right here, high energy. This is low energy. And I expect you to know that blue is more on the high energy and red is more on the low energy. Even though it's violet on that side, I'm happy with it. You do need to know these terms: gamma rays, X-rays, ultraviolets, infrared, radar, and or is microwave. Shortwave, we'll call that microwave. You need to know those ones. Relative to each other. Yeah. Eight to 10 to the minus 10. I don't need you to remember the numbers, but I need you to know that infrared, sorry, we're talking about infrared, right? 10 to the minus 6 to 10 to the minus 4. But I need you to know that infrared comes after red, right? Because all this here, all this, is squished into this little tiny thing here, right? And this is above red, this is above the ultraviolet, infrared. What's crazy is that we are only able to see within this tiny little slither of spectrum right here. We don't see anything here, we don't see anything there with our human eyes. We can see it with machinery, and other animals can see a different spectrum. But our human eyes can only see this spectrum. A very narrow range of like 400 to 800 nanometers for a wavelength. Anyways, back to why I was talking about all this. The different wavelengths will mean that the light is going to travel at a different speed, right? In air or in vacuum, they all travel pretty much with the speed of light, right? But they all have a tendency of slowing down more or less depending on the medium that they're in. And so if they're all traveling at a different frequency or a different velocity rather, what ends up happening is they'll refract at a different angle, right? Because remember, the angle of refraction has to do with the angle at which it comes in, but also the velocity of it. So look, if everything's coming in at the same wavelength, right, at the same, not the same wavelength, the same speed, and hits this prism and then refracts at a different speed because they all travel at a different speed in different medium, then each color is going to refract differently. So it's going to split the beam of white light into its color. And that's what you see like this classical prism thing, and that's why you see a rainbow. So in the case of a rainbow, what you're doing is the raindrops are actually doing what the are doing the dispersion, right? And in this case, it's a prism that's doing the dispersion. this is a kind of super simplified diagram of what a rainbow dispersion looks like. But what's cool is that sometimes when it's been a rainy day, you look in the sky, you don't only see one rainbow, you see two rainbows. And the second rainbow has its colors flipped around. And the reason for that is because, so here you have the first rainbow, and you can see that the violet is coming out on top of the red, right? So you're gonna have seen it in a certain order on the rainbow. But if you have like certain conditions met, I mean, I'm not a meteorologist by any means, but let's say this is a water droplet. Instead of the light going in like this and coming out, so here's your violet and here's your red, right? Instead of that happening, what's going to happen is you're going to have total internal reflection. And so this is your violet here, and this is your red here, and then they're going to cross over. Okay? And so now you have red on top and violet on the bottom. That's what you say. And so you have the regular rainbow, and then you're going to have the total internal reflected rainbow. So you're going to see two rainbows in the sky, and their colors are going to be inverted. See that there's a primary rainbow and a secondary. Neat stuff. Next time you can explain that to someone. And that's called dispersion. That's what I need you to know about it. Yeah. So that would have to do with lenses and curved surfaces. Are we going to do that today? If we have time, we'll do that today. Yeah. Remember that question and bring it up again, okay? Okay, so this is the summary. And it's a good time to take a break, I think. Yeah. So like 5 minutes to fill this out. I'm going to also post the answers to this online because it's the best thing that you can use to remember which one's which. But I want you guys to fill it out on your own for right now. And let's say you do that and you come back at 11:15. Come back at 11:15, right? So fill that in and come back at 11. Make a glass of water. Use your definition. What is it? How are you going to remember it? I'm never going to ask you to recite it word for word from my slides. But if you were to have to explain it to someone, how would you do it? So maybe your definition could include a drawing. That's okay. Remember, it's for you guys to remember this. We're actually a bit ahead of the schedule. Come back at 11:20. All right. So what we did this morning so far was supposedly supposed to help you for your lab that's going to be tomorrow. This lab is going to help you for the lab that you did yesterday, right? So hopefully you have everything that you need to do those two labs. If we don't make it in time and you feel like there is a subject that we still haven't covered, come and ask me. It's still supposed to be, the whole lab is supposed to be reviewed, so I'm not sure about that. But I think we should get through it. Come and ask me if there's anything you want. No question, Max? Yeah. Did I write 3:45? I meant 5:45. Sorry about that. All right. So now we're going to talk about mirrors and lenses, and it's going to be basically exactly what you guys did in the lab yesterday. There are some basics that we need to remember. We need to remember that mirrors reflect light and lenses refract light. All right, those are the two major properties that we worked with yesterday, and there are the two major ones that you need to know for this here. So I put this in. I mean, we just went over it. I'm not going to explain it again. Basically, the law of reflection is that the incident angle is equal to the reflected angle. There are some characteristic conventions that we need to remember. All right, so actually even easier than this would have been if I showed you the formula. Do you guys remember this formula? So this one hopefully rings a bell. It's the major formula that we use for both curved lenses and for curved mirrors. And you can also use it for anything. You don't have to use it for just curved lenses, curved mirrors, flat mirrors, and the thing still applies. So what does it mean when the image distance is greater than 0? Does it mean it's virtual or real? Remember this? Real, exactly. And if it's less than 0, then it's the other one. It's going to be virtual. So here we can write down real image. And here we're going to write down virtual image. All right. What does it mean when the height of the image is greater than 0 versus what does it mean when the height of the image is less than 0? So basically, what happens if the height is positive or what happens if the height is negative? Inverted or not? Which one is inverted? Negative or positive? Negative, yeah. So this one is right side up, right side up, and negative would be inverted. Sorry? Not necessarily. If we have only one lens and one mirror, yes. But it's once we combine two lenses, let's say, not necessarily. Okay. And lastly, what does it mean if the absolute value of HO is greater than the absolute value of HO? The height of the object is greater than the height of the absolute value, ignoring whether it's inverted or not. We're talking about it shrinking or being magnified. Yeah, in this case, it would be shrinking. All right. What's the opposite of magnified? Shrinking sounds awful. Demagnified, is that a thing? Looks smaller. Let's go with that. Looks smaller. And if HI was greater than HO, then it would be magnified. And it's also possible that HI is equal to HO, in which case it's just the same size. So far, so good? If I were to take a sphere, and I were to, on this side of the sphere, make the outside, or sorry, make the inside of it shiny, or the inside wall of this side of the sphere, I'm going to make it shiny. On this side, I'm going to make the outside part of the sphere shiny. Okay. What I have is a convex and a concave mirror. If I were to look at it like this, where's my eyeball? Yeah, if I'm looking at it like that, then I see the shiny part of the mirror, and it's a curved mirror. And if I'm looking at it like this, then I see a convex mirror, right? And so we learned about how these convex and concave mirrors have these focal points. And in fact, if I were to leave that convex and concave mirror as a sphere, right? Because you guys didn't have it as a sphere, you guys just had it like a part of a sphere. Like let's say I cut it here, right? And I took this chunk out and I gave it to you. That was what you guys used, right? This thing has a focal point, F, and it also has a center of curvature, C. And the center of curvature C is if it were still a part of a sphere, then the center of that sphere would be the center of curvature, right? And it also just so happens, if it's a perfect sphere, that C is equal to 2F, right? Or 2 times the focal length. So the focal length is actually halfway to the center of curvature. I'm going to write that here. So that's F, and this is 2F. Obviously, that's not how all spherical mirrors are made. I mean, this is a perfectly spherical mirror, but like there's chances of using a perfect sphere to do this kind of work. Like the ones that you guys might use to apply makeup in the morning. You guys know what that one? The one that makes your pores look gigantic. Those ones are not a perfect spherical mirror, of course. They do the job, and that's good enough. It costs you $5. If you wanted a perfect spherical mirror, you'd be spending in the thousands and maybe tens of thousands of dollars to get that quality of work. But it's not what you need. That's why it's not a perfect sphere. So far, so good? Yeah? Okay. All right. So there is a few rays that we need to consider when we're doing a ray diagram of a spherical mirror, right? I've color coded them. Did I put the colors on the thing? Yes, I did. And so let's say I have an object, and I want to find out where its image is. on a curved mirror. So there's three rays that I have to draw in order to find where that image is going to be located. You only need to do two of them, but there's three important ones. So if you choose which two you want to do, you should know how to do all of them. All right, so the first one is through the focal point, right, and then parallel to the principal axis. Yes, if I didn't mention it yet, the principal axis is this here. There's here. That's the principal axis. Principal axis. Okay. And so which one of these rays, as you see here, is through the focal point and parallel to the principal axis? There it is, right? Let's say this was A, B, C, D. Which one? D, yeah, exactly. So D is going through the focal point, and then is parallel to this line here. Okay? That's an important ray. The second one is through the center of the mirror, and I didn't write it really well here, so I'll write a second note for it. Through the center of the mirror, and just using the law of reflection. So incident is equal to reflected. And so if it's going to the center of the mirror, the angle at which it bounces off is going to be the same angle as its incident. So which one of these rays is that one? I just pointed to it. C, exactly. And the third one is parallel to the principal axis and through the focal point. So which one is that? So here they are identified. Where those rays converge, where the reflected rays converge, that's where the image forms. Okay. The point that there is the reflected rays that converge, that's the most important. Okay. So an image only forms when the reflected rays converge. If a bunch of incident rays converge, there's no image being formed. It's where the reflected rays and I drew this for a concave mirror, but it applies for anything. It applies for convex mirrors, it applies for biconcave and biconvex lenses as well. Okay, so we're going to remember these, we're going to practice them all. Just looking at this, what kind of mirror do I have? Concave mirror. Is this a converging or a diverging mirror? Converging, because look, this one, let's take ray B for example. Ray B is going parallel to the principal axis, and once it's reflected, it goes towards the center, so it converges the ray, right? If it was a diverging ray, it would hit the mirror and go away from the principal. Right? Alternatively, look, I'm looking at the one that's going from D. From D, the blue one. It's going away from the principal axis, and then it gets parallel to the principal axis. So it's still converging. It's still getting closer to the principal axis. Okay? That's why we call this a converging mirror. A diverging mirror will do the exact opposite. We'll do examples of that when we get there. So you have to remember this two equations. All right. I mean, I'm going to give you these, but you can. So this is the one where it relates the focal point to the distance of the object and the distance of the image. You should be using this a lot for your lab that you did yesterday to calculate theoretical values. And another important one is the equation for magnification. So magnification is going to be the distance of the image divided by the distance of the object, like at the minus sign, or the height of the image over the height of the object. And there's no minus sign for that one. What would the units of magnification be in this case? What's that? Yeah, it's no units. All right. You have to have the distance of the image versus divided by distance. Meters divided by meters is no unit. Okay. The magnification has no units. There is a difference between converging and diverging lenses. So here I wrote that f is negative. Here I wrote that f is negative for also negative for biconcave lenses. So let's add that. Right? And this f is being positive for concave mirrors is also true for biconvex lenses. What do convex mirrors and biconcave lenses have in common? Yeah, they both produce virtual image. What did you say in here? What's the opposite of converging? What's that? Can someone help her out? Diverging, yeah. So what's common is that they're going to produce, well, they're going to produce virtual images because they're divergent. So let's write that here. This is divergent. This is convergent. All right, now let's talk about magnification. What does it mean if magnification is greater than 1? Magnification is greater than 1. Was what? Was magnified or enlarged, right? So if it's greater than 1, it's magnified or enlarged. What if it's less than negative 1? Smaller and inverted. So give me a number smaller than negative 1. Any number smaller than negative 1. That's bigger than negative 1. Minus 2, right? That's smaller than negative 1. So is that magnified or is it shrunk? That's actually magnified. It's inverted and magnified. So if the absolute value of magnification is greater than 1, then it's magnified. Okay? And the negative sign indicates whether it's flipped around or not. All right, now we know that. We can do some problems. Can we talk about this now? Yeah, sure, why not? If I have the function here, 1 over f is equal to 1 over di plus 1 over. And I was talking about a curve here, and f represents half of the distance to the radius of curvature, right? And I'm now talking about the focal length of a flat mirror. Now, how is that possible? How is a flat mirror have a focal length if it's half of the center of curvature? It's flat. It's not curved at all. How would you answer that question? Let's draw a circle. Here's a very small circle. Small circle with the center of curvature in the middle. Okay. Is this a curvy mirror? Pretty curvy. Compared to this one, which one is curvier? This one is curvy, right? It's more like this. This one is more like this, right? So this is less curvy. What about this one? That's less curvy. How curvy is flat? Not very curvy. So let's say you're talking about an infinitely large sphere, and essentially it just looks like this. right? And the center of curvature is where the moon is over there, right? Now is my mirror flat? Close to flat, right? But if my focal point or if my center of curvature was at infinity, what's half of infinity? Infinity. So where would my focal point be if I had a flat mirror? It would be at infinity, right? Because the center of curvature is at infinity distance away, right? And that's why I'm getting this flat edge here. And half of the infinity, which is where my focal point is supposed to be, is also at infinity. All right, so that means I have this equation here. 1 over infinity is equal to 1 over di plus 1 over do. What's 1 over infinity? Yeah. So 0 is equal to 1 over di plus 1 over do. And let's do some algebra. I'm going to move 1 to the other side. So it's going to be negative 1 over di is to 1 over do. And I can inverse each side and say that di, or negative di, is equal to do. Yeah, so whatever the distance of the object is in a flat mirror, it's going to be the same distance on the other side for the image. Simple as that. And what is the focal length here? We're going to say, we said here is infinity. And is the image always going to be negative in a flat mirror? Always going to be negative, right? Because if the DO is positive, then DI is always going to be the opposite sign. That's always going to be negative. So if DI is negative, is it virtual or real? Right. So for a second. You can always consider a flat mirror as a curved mirror with a humongous focal point, infinite. All right, let's do some ray diagrams and practice what we just talked about. The 3 rays that I mentioned before, you're going to need them right now. All right, so it's parallel to the principal axis through the focal point and principal axis, and then to the center and reflective. So let's do this one together, and I want you guys to do the next one. So here we go. I have, there is a parallel to the principal axis and through the focal point. If you have a ruler, this is perfect. By the way, if you don't know how to, you will need to know how to use a protractor for this part. You know what a protractor is? No? Okay. So if you don't know how to use one, come and see me. You don't need to bring one. I think the lab has got enough to give you a junior test. All right, so that was the first one, parallel to the principal axis and through the focal point. Let's do the next one, which is through the focal point, and parallel. Right. I should do it in a different color, actually. And the last one is to the center of the mirror and then reflect to the same angle. This is a correct one. Notice that my 3 rays coincide in one spot. That's perfect. If yours didn't, you drew it wrong. So there is my object. So here it was pointing upwards. So here it must be pointing downward, right? So look at it as an arrow. We just did the point of it. If we were to do every single point along this arrow, and break it up into little particles, let's say. let's say we broke this arrow up into little particles like that. So what we would get is something that looks like this. That means my image is inverted. My image is inverted. Over there. Tell me about the quality of this image. Is it virtual or real? In this case, it's real. Is it smaller or larger? Is it, sorry, shrunk or magnified? Okay, we're going officially with that term. I can't find a better word. Shrunk. Let's just be shrunk. Is it inverted or right side up? If I were to give numbers on this, you should be able to do the same thing. So if I said, for example, focal length was at 10 centimeters and the object was at 40 centimeters, 400 or 40? What would the distance of the image be? Then you can use 1 over f is equal to 1 over di plus 1 over do. It should give you roughly, according to this, 13 or maybe between 10 and 15 centimeters. Can you just do that? Make sure we get something similar. That's a way we can check our work. If I wanted to give it a height, let's say the height is 10 centimeters. So HO is 10 centimeters. So 1 over di, 1 over f is equal to 1 over di plus 1 over do. 1 over 10 is equal to 1 over di plus 1 over 40. So my di should be 40 over 6 centimeters, which is equal to, I don't know, 20. What is it? 20? Oh, 13. Oh, okay. I was right. It's a positive number. That's how I know it's real. If it was a virtual image, it would have given me a negative number. If I wanted to find the magnification, I can do minus di over do. So it would be minus 13 over 40. Because that's going to give me a positive number. Sorry, negative number. What's the value for that? 13 over 40 is going to be 0.3. 0.3? So negative 0.3. So is it positive or negative, my magnification? Negative means it's inverted. It's also, is it the absolute value of the magnification? Is it less than 1? So that means it shrunk or it magnified? Shrunk, and that's what we see here. So we confirmed it both with the ray diagrams and with the formula. Make sense? Okay, perfect. Let's move on. I can also find, if I gave you the height of 10 centimeters, you can also find the height of the image using the magnification. You can find it, right? Just remember, it's HI over 18. All right, this time I want you guys to do this one. It's a bit harder though. All right, we're already jumping into like one of the harder examples. Remember the 3 rays? Just do them, and we'll talk about how they converge later on. This class ends at 12:30, right? What's the fundamental difference between a mirror and a lens? Or just if I were to ask you, what's the difference between a mirror and a lens? One can reflect light and the other one refracts light. Which one allows light to go through? Right, so keep that in mind when you're doing all these problems. Mirrors let light reflect. Light cannot go through a mirror, right? But it can go through a lens. I'll start with the easiest one here. It's towards the center, and then reflected at the same angle. Is this a divergent or a convergent mirror? Diverging mirror. So if my ray hits my mirror, it needs to diverge. It needs to go away from the principal axis. So if I were to draw a parallel ray like that, a reflected ray should be away from the principal axis. How do I know? So if it's parallel, and what's the rule where rays that are parallel to the principal axis, they go into which direction? Towards the focal point. The focal point's all the way on the other side. And we know it's a mirror, and light cannot go through the mirror, right? Or the mirror is opaque. So the light's going to go there. Which direction is going to reflect? Away from the focal point. So you would draw it like this. And the last ray that we talked about was towards the focal point and then parallel. But the focal point's on the other side, so that doesn't really matter actually, because I'm going to go towards the focal point, and when I hit the mirror, I'm going to go parallel. That was bad drawing, but there we go again. So that's weird. Look at this. Right? This reflected ray, this red reflected ray, and this blue reflected ray are diverging from each other. Confirms the name divergent mirror. And remember, where does the image form again? How do I know where the image is forming? What's the rule? Yeah, it has to be where the reflected rays meet. Are these reflected rays meeting? Well, they're not meeting on that side, but if you work backwards, they'll meet. Let's try that. So if I were to work backwards, I kind of cheated to make it work. What do you notice? It's a virtual image because no real reflected rays converge there. All right, my reflected rays, these rays never went through my mirror. So I couldn't capture this image on the screen if I wanted to. If I put a screen, if I put my eyeball right there, would I be able to see that image? No, I wouldn't, because there's nothing actually there. So we call this a virtual image. Virtual image. So if I were to say, complete this. What would you say? I'll have to put mathematical symbols in between these. So this is, what is VI compared to 0, HI compared to HO, absolute value, and the absolute value magnification compared to 1. So for the first one, what do you guys think? Negative, it's smaller than 0. What about the height of the image compared to the height of the object? Small. What about the magnification compared to 1? How would you compare M compared to 0? Bigger. It's positive because it's right side up. So if I were to do my calculation, we know that my magnification is greater than 0 and less than 1. So we already narrowed down what our answer should be when we do it mathematically. That's good. For a flat mirror, it's pretty much the same thing, all right? But this time, all we're obeying is the law of reflection. All the incident rays have to be equal to reflected rays. So here, I chose to draw 3. Let me draw a million more. Let me draw another one. If I were to draw this incident ray, the law of reflection says it has to reflect at the same angle, so it goes that way. And if I work my way backwards, check that out. It goes towards where this other ray diverge. Let's pick another ray. I'm going to be really exaggerated here and go like all the way over there. If I go all the way here, this angle has to be equal to the reflected angle. And I can work my way backwards. It'll still go towards. That's how I find the image location for a flat mirror. All good? If this distance was DO, also DO, and that's DI, right? So your DI is going to be equal to DO. Is it virtual or real? Are they real reflected rays that are converging here, or is it working backwards of reflected rays? I have to work backwards to get these ones, right? So I know it's virtual, so it's going to be actually negative DI is equal to DO. And that makes sense because we proved it not too long ago when I used the other formula. All right, let's move on. That's it for mirrors. I thought I had more for mirrors. Oh, they're after the question. Okay, let's go to lenses and then we'll come back. We're going to use the exact same principles, same formulas, same equations, same conventions, same 3 rays that we need to draw. All of those apply for lenses as well. Simple. If you think of a lens, a thin lens, as 2 spheres, it's going to have 2 focal points, right? So if I were to say, two spheres like this, look at that. There's your thin lens. The biconvex or biconcave? Biconvex. It's convex on both sides. Each side has its own center of curvature, and therefore each side has its own focal point, right? And if it's symmetrical, you can say that this focal point is equal to this focal point, right? And in this class, we're only going to be focusing on those that have equal curvature on both sides of the lens. So we can say that this, normally we call one of them F prime and the other one F. We can say that F prime is going to be equal to F. Okay. if it was a thick lens, right, we would have to use Snell's law. Remember Snell's law is N1, SN1 angle 1 is equal to N2 sine theta 2, right? And we'd have to do it here, and we'd have to do it here. We'd have to find the tangent of the surface, draw the normal line, find this angle, and then find this angle, and that would be our the way we would do it for a thick lens that has a curvature. However, in a thin lens, right, and this is what the thin lens approximation is that light rays will refract right through it, right? It doesn't have enough time to correct itself on the inside. It just bends it and that's it, right? So here it bends it, and it bends it again. Here it just bends it once. Any questions on that? So again, we use the exact same equations for these. Nothing's changed. The conventions are all the same. Now there is one fundamental difference. We said in mirrors, light does not go through. So if an image is on the same side as a mirror, we call that real because it's supposed to go through. I have a curved mirror, and here's my object, and I have an image that formed here, let's say. There's my image. That's a real image because it makes sense that the image is on the same side of the mirror because it reflects the rays. Right? If I had an image back here, it would be virtual because it doesn't make sense that an image is forming behind something that's opaque. However, in a lens, it's the opposite. If you have an object here, where do you expect the image to be if it were real? On the other side or on the same side? Other side. You would expect the image to be real on this side. It makes sense. Light has to go through the lens. If I end up with an image here, well, that doesn't make sense. The light didn't even go through the lens yet. That doesn't make any sense at all. That's how you know that's a virtual. Okay? So it's the opposite. That's the main and only difference between mirrors and lenses. Yeah? Okay. Knowing that now, let's just do some of these. This is what I was just saying. Lenses allow light to travel through them. Mirrors reflect light, therefore don't allow light to go through. All right, it's like really fundamental here. I have some convention to show you guys, just because they don't always show lenses like I did here. So this is going to be a biconvex lens, and the way I remember it is like this. So it's a line with arrows pointing upward. And this one here would be drawn like that. So you can think of that as a biconcave lens. I'll just draw that here as well. Okay. So bicon. So I won't always be drawing my lens as a curvy surface. If I draw the arrows, you know it's a curved lens. All right, back to basics. Let's go and try to do the ray diagram for this. Remember your three rays through the focal point and parallel through the focal point, and through the lens without any refraction. And again, remember that you want your rays to go through. And because this is a biconvex lens, is it a converging or diverging lens? Divergent? Convergent? Convergent. This one's a convergent lens. So you know you did things right if your rays are converging. If they're not converging, then you do the same. So normally for the mirror, we had one that hit the center of the mirror and reflected. What do you think that one's going to be equivalent on a diagram with a lens? Is that? Yeah, we'll just go straight through. So that's going to be an easy one. Straight through, no reflection. Then it's parallel. Oh, we should do a different color, right? Parallel and through the focal point. And it has to go through the lens, so I know which focal point to choose. The last one is through the focal point and parallel. Look at that gigantic dot I found converging all my points. I cheated, sure. But it's supposed to converge on one point if you did it with a ruler. This will work 100% of the time. It'll always converge as long as your distance for the focal lengths are equal. Make sure that your two apps here are exactly equal. If you do that, then your points will converge on the same point for sure. Right? Because remember, there's no curvature to be drawn. We drew the lines of a straight line. There's no ambiguity there. That means that my image is formed upside down there. Is it smaller than my object? Smaller than my object, inverted or up to right side up? Inverted, real or virtual? Real, because I need, it's a lens, my image has to be on the other side, and it is on the other side, so therefore we're safe, it's real. Good? What happened? What slide are we on again? We're here? Yeah. There we go. All right, let's do the same exercise. This time it's going to be a diverging Good luck. Let's start with the easy one. That's the easy one. Next one is parallel. Color. As a divergent lens. So if I'm going through this lens, what should it do after hitting the lens? To diverge, or should it go upwards or downwards? Upwards. How upwards does it go? It has to be parallel and through the focal point, right? So which focal point is this going to go away from? From here, yeah. So it would be this way, backwards from that focal point there. I already know where my image is going to be. But let's just do the third ray so we understand what's going on. The last one is going to be towards the focal point and then parallel. So it's going towards this focal point or the other. F or F prime. Yeah, it's going to go towards this. It's not going to reach it, but it's going to go towards it. And then parallel. And if you did it right, and you work back from your refracted rays, so the images form from refracted rays, not from incident rays. So if I work backwards, I should have the image right there. Is the image real or virtual? Virtual, because I'm supposed to go through the lens and I didn't. That's weird. Is it right side up or upside down? Is the m greater or less than, or the absolute value of m greater than or less than 1? Less than 1. And for all these situations, you could have just used the formulas to figure it out as well. Just the same thing. There is something that I need you guys to understand, however, because it's going to make the next section a little bit easier. If I go back here, going back to this, right? All this is for nothing if there is no observer. Okay? If no one's looking at this, who gives a damn if the light rays? We need to be able to see something. So in this case, where do you think the observer is? On that side of the mirror or on this side of the mirror? On this side of the mirror. If I was on this side of the mirror, I wouldn't see anything because the mirror would block my. If I was on this side of the mirror, I can see stuff and I'm and I would see the image on the correct side of the if it was the real image, I would see it on the correct side of the mirror. So in this case, if I were to draw an observer, I would draw an observer here. Okay? Same thing for this. Again, it's a mirror, so I need to draw my observer. And my observer is going to be there. If I drew it with a lens, now we're back onto this situation, where would my observer be? On the left or on the right? All right. My observer has to be here because if I was here, don't draw it on the left. If I was here, then I would see my object, but I would never see my object through the lens. And the fact that the lens is there is now useless, right? Looking at that. You get it? All right. And the same thing here. Right? Observer should be on the right. Okay. Let's do one last example, and we'll do some quantitative. We'll finish off with these 3 examples. Go ahead with this one. Let's start with the easy one. Oh no, it's not a mirror, it's a lens. parallel to the focal point. The last one's kind of tricky, right? Through the focal point and parallel. So how do you get through the focal point before hitting the lens? You have to use this. You have to use this focal point, right? So it's going to go towards that focal point, but it's never going to hit the lens now. It's going to work with that. My drawing is bad because my lens is not big enough. So it's going to go in that direction, and when it hits the lens here, it's going to go parallel. Or parallel on the other side because it's a lens. Okay. Now we got to find where the image is. So we have to work backwards from the refracted rate. Remember, it's always a refracted and a reflected rate. So this one's going all the way back here. This one's going all the way back here. This one's going all the way back here. So there you go. There's my image. That image larger or smaller than my object? Larger, right side up, virtual or real? Yeah, virtual. When you're using a magnifying glass to look at something, what situation does it represent? First of all, is it a lens or a mirror? Is it biconcave or biconvex? Anyone have a magnifying glass? Is that still? No. There are some that are like that, but they don't magnify. They retract. So it's a biconvex lens. But we saw, so this example made the image bigger, right? But before, when we were doing we did this one here, this one made the object upside down and smaller. So that's not the situation. It doesn't make an object smaller, and it definitely doesn't make it upside down. You look at something through a magnifying glass, it makes it bigger and it keeps the orientation, right? So that would mean that it's this kind of situation where you're looking at the magnifying glass really close to the object. So the object is actually between. So you're looking at it from here. Your eye is going to be here. The eye is going to be here. You're looking through the magnifying glass. The object is between the focal length and the lens. That's why it's really close to. And if you were to pick it up and look at something distant, what do you notice when you're looking at a magnifying glass? Everything is flipped. Everything's upside down and very small. Right? Does anyone have a magnifying glass? You guys don't keep them just like that? Your glasses, it's funny that you should use that. Your glasses are a combination of convex and concave. So they're not biconvex, they're different on both sides. Put your glasses in front of your eyes in a distance. Yeah, yours are actually kind of biconvex. Yeah, you're right. Could you show me the same thing as yours? Just hold them up to your eyes distance. Yeah, so it makes those a bit smaller. But anyways, if you look at them, they're much more complex. And there might be something like this, with different curvature on both sides and different types of lenses on both sides. It can be concave on one side, convex on the other side. All right. We're going to talk about glasses next week. Did I tell you we're doing an eye dissection? That means we're also doing the whole biology of corrective measures. The glasses, contacts, laser eye surgery. Okay, so here's the mathematical problem. Go ahead, do that. Actually, do question 4 and 5. Once you're done, you can go. or if it's 12:30, or you can go now if you want, whatever you want. But these are the questions that are associated with it. And again, I'm not be dry as water.